Let's welcome Chris Waters. Thank you.
Hello. I'm Chris Walters from Pinterest. I've been at Pinterest for the last 2 years. I'm the tech lead of our anti-spam efforts. And today I'm going to talk about some of the history of what spam has looked like on Pinterest, what lessons we've learned from that, and then how that's influenced our technical approach. I won't have time, unfortunately, it's only a half hour, so I won't have time to talk about the internals of a lot of these systems. There's some pretty fun stuff. Hopefully I'll be able to talk about those in the future. So I'm going to focus mainly on capabilities of the system. What are the design objectives? Okay. So first of all, probably everyone's familiar with Pinterest, but just in case not, it's a discovery engine. Can you hear me? To discover things they love and do them in real life. The mechanisms are you have a pin, which is a visual representation of a real-world object or a place on the internet. These are then herded into boards, which are user-curated, so they're presumably conceptually related in some way, which is actually the power of the recommendations engine, is that it's this massive human-curated collection. And then those boards can be particularly useful to spammers, is you can get very high distribution through group boards, which you've got a lot of followers, a lot of collaborators. Okay, so one of the questions that I've been asked over time, which is actually a good one, is does Pinterest have a problem with spam? Years ago, the answer to a lot of people is obvious. Now, hopefully, it's less. But let's go through a little bit of why it is actually so attractive to spammers. So step one is we have amazing scale characteristics for the attacker and for good users as well. But you get it's almost exclusively user-generated content, which means that the ability to get a massive amount of uncurated, unmoderated content into the system is easy. That's what it's designed for. It also surfaces forever, so there's very little time it's not usually time-bound. So you put a piece of content into the system, and if we fail to find it, it's going to pay you for a very, very long time. It's an advertisement for spammers. I think this is going on YouTube or something. So it also has high fan-out, right? There's a lot of ways that you get a single pin into the system, and then it goes out through category feeds, it goes out through all of your followers' home feeds, it goes out through search, a lot of different ways. And in fact, some people don't realize that spam is spam and will repin it for them, giving them extra distribution. Also, because of the mission, because of what we design the system to be, this discovery engine, the content that we surface is usually pretty good, which means that users come to trust it and they also engage with it at a high rate. Our users are attractive from a demographic standpoint and often reflect purchase intent, which is to say that for the exact same reason that it's a good business for us, it's a good business for spammers. It's a zero-sum game, and when we fail to remove malicious content, pinners suffer. That's why we're here. So what does it look like on Pinterest? Every platform is a little bit different, right? Email spam is going to look a little bit different than social network spam, which is going to look a little bit different than Pinterest spam, which looks like this. So you've got examples of, how does this work? Oh no, there's no laser pointer. So on the far right, that's an example of a work from home scam. Actually, we call that the MSNBC pin because it would link to a fake MSNBC or BBC looking site that would say, hey, get rich by giving us $100 and we'll let you stuff envelopes and so on. They make it look legitimate by linking to MSNBC and then take your money. And then there's a bunch of other ones. You've got various forms of weight loss spam, gift card scams, there's fake products, in that case Nike, Rolex, and so on. Okay, so the history of where we've come from and how we've arrived at where we're at is, in the early days, it was all about fires all the time. Pinterest blew up very quickly. I wasn't at the company at this time, but it blew up very quickly, and spammers immediately recognized that this is an opportunity for them. That Starbucks gift card that I had was the first example of they were just flooding the feeds and there was no response. And so the early days were basically characterized by, the very first response was this thing called shift clicking. Shift is in quotes because the F is not usually pronounced internally. But it's as manual as it gets. You hold down the shift button, you click on a pin, and then it deletes the pin, it removes the user from the system. And it allowed the early team to move very quickly, but it also did not have good scale characteristics. This moved on to having Hive queries, which is, Hive is our system for, if you're unfamiliar with it, it's basically a SQL engine for large data sets. So we would lower our event stream, the record of everything that's happening in the system, to Hive each night. then you can run a query on that. It actually was so expensive, we really only did it every 2 weeks because you have to then run the query and then babysit a script. It's a massively painful process. It's also based on a very simple signal. And actually, because it was so painful and we did it only every 2 weeks, it actually probably helped that we were using a very simple signal for them to not find it, because if they changed a single pixel, then it would have disappeared, right? We would have been back to square one, which is a larger lesson. Read the Facebook Immune System paper for more information on that. So the next step is to get synchronous enforcement, which is hacky rules strewn throughout the code base. It's a Python code base originally. And so this got us to a place where we had some form of synchronous blocking. When I say rule, I mean it's a signal that indicates that this is a spammer and this is not a spammer. Simple example, this would be a bad rule, but logging in from a certain IP block might be, we know that that's some attacker's data center or something, so indicate that that's suspicious. Okay, so now we're going to talk about the systems development. So at this point now we've got our hacky rules that are spread throughout all of our API front ends or search index clusters or wherever someone is interested in filtering spam, which is say where we would go in and write those rules. But what we want to get to is, and it has some problems I'll talk about in a second, what we want to get to is we want to get our analysts into the fight, our spam operations team, our beloved spam operations team. We want them to be able to interact with both synchronous and asynchronous enforcement. So this is where we started. Here's where we want to go. Let's go step by step. So step one, we've got the problem that it requires a full fleet deployment to get this done. Synchronous rules are hard to maintain and written entirely by engineers, so there's a very expensive coordination process between analysts and engineers at this point. Plus, there's no asynchronous enforcement. So step one is to launch the SpamService, which it has the nice benefit that we now no longer have rules strewn throughout the code that we're probably going to forget about. We have them all corralled into one place. It still requires relatively expensive coordination between analysts and engineering, but at least it's in one place. And when we do a deployment, we only need to deploy to our one service as opposed to trying to get everything everywhere deployed. Step two is to introduce Stingray Async. This is the pipeline that allows us to, so the front end, which is producing these event objects, which somebody clicks on a pin, somebody does a search, somebody does something on the site, usually creates an event object. This is now getting pushed to Kafka, the LinkedIn message bus, which is kind of the lifeblood of communication within Pinterest. And then that is going to be considered asynchronously by a system called Stingray that has a rule engine at its core. So this is nice because now we have the ability to experiment with asynchronous. Because it's asynchronous, we don't have to worry about latency characteristics up front. We can experiment with the model. We can figure out with the DSL, that I'll talk about in a second. We can experiment with how should that look, and we can do this all offline. We can have backups of the queue for hours, and we can just prototype correctly. But we still have this problem where the synchronous enforcement is lower quality than it could be. So step three, of course, is to introduce the synchronous pipeline. So at this point, every single rule update is deploy free. We have visibility into all actions taken by the system. There's very little coordination between analysts and engineers on any particular attack. There's a high amount of coordination around other things, but mitigating any particular attack requires very little effort. We sit together, we go to lunch together, we go to Vegas together. We coordinate a lot, but on any particular attack, we need to be able to move quickly, which is the point of this infrastructure. So this is the state of the system today. We'll talk about what the future holds as well. So some scale numbers. 1.3 billion events per day are being considered synchronously and asynchronously. About 100 rules live at any given time. 5 to 10% of those are churning on any particular day, meaning not necessarily is it like a brand new attack, but there's some sort of mutation that needs to be accounted for. And we're taking over 1 billion actions. This is not all spam. That would be an enormous amount of spam energy being put into the system. It's because other groups have started using it as well. I have an email to the keynote's point. It's actually pretty useful infrastructure. So we've got email experimentation platform, notifications platform, ad quality enforcement, and many others. So let's talk results, right? That's why we're here. That's why we get paid. This is a pin reports graph of the last 3 years. It's important to note that this is actually, it's kind of cut. Oh, it's not cut off over there. It's important to note that this is on an absolute scale. So even though the user base has grown exponentially, it actually means that a flat line is better on a percentage basis. So these are the major milestones. Some of them correlate directly with drops, but mostly I would consider they all add up to this tail end here, which is
consider this essentially to be in the noise at this point. So any particular attack is unable to, for the most part, gain enough of a foothold on the system that it even shows up in this metric, which is great, but it also means this metric is not all that operational. So at this point, which is good. It was a good metric to start with. We've had to get much more sophisticated. If I had more time, we spent 2 years thinking about the metric problem. Unfortunately, I don't have time to talk about that, but maybe in the future. So the things that we've learned from this process and some of the things that we sort of set out when we were kind of taking the original architecture and moving it to the new one is that, number one, make systems that product teams want to use, right? You'll catch more flies with honey than with vinegar. If a product team wants to build something, our answer should be yes, not no, even if, I'll give you an example, our messages platform was 6 or 8 or 10 months ago, something like that. They wanted to add the ability for a user to say, hey, I want to send a pin or a board to a friend from my contact list. Right thing for the product, right? Pinners want to do it. There's viral characteristics that are useful for the product. But the alarm bells are going off that, oh my God, this is a huge vector, right? I could just be a spammer, and if you haven't figured this out yet, spammers, here's what you can do. Upload what looks like a contact book, and then use us as a relay to contact anyone you want, right? That's a potential disaster. So I want to say no so badly, but we don't. We say yes. And we do this, we basically have empathy for our users. We figure out their job, they don't care about spam, right? We're, as was mentioned earlier, like we are a plumbing team. If we do our job, people don't know we exist. Not only users, but even internal customers. So we try to simplify the hard problems behind simple interfaces. So we just say yes, give them a very simple interface that hopefully is pretty much the same. It's hardening over time to all the teams, and then we solve the hard problem behind the scenes, and they just largely don't know that it's happening. Step 2, scaled effort. The attacker is exerting scaled effort, and we should as well. That early example of the shift clicking was it was the right thing at the time because there was just an ongoing disaster. But the problem is, you'd spend 99% of your time in fire mode and 1% looking forward. Well, you want to start getting that to, 95-5, 80-20, 50-50, and now we're pretty close to like 99-1. I mean, at least on the engineering side, the things that we're working on are rarely because there's some raging fire happening. Also, you want to apply lessons between mutations, right? These attackers it's not a de novo attack. It's not from first principles every single time. You want these people to have to work very hard to mount an effective mutation, the next phase of the attack, and you want it to be very cheap on us. So we want to take as many lessons from one attack to the next as possible, including infrastructure lessons. The goal of all of this is that we want to scale Pinterest 10x. Like I will consider us a success if we can scale Pinterest 10x and we have basically the same size team, which is to say 3 analysts, 8 engineers, I believe, plus SpamOps manager and eng manager. Theme 3 is speed. This is definitely the most important part. The attackers are here to make money, and the more that we can shorten the amount of time that they can make money, the less attractive we are to them. Hopefully they end up bleeding money and running out of it. This is because of the adversarial dynamic, this cat and mouse game, there's perpetual novelty. We always see an attack is always new in some way, otherwise it wouldn't be an attack. This means that we need to develop rules quickly and enforce them as close to live as possible and clean up. So let's dig into this. I could talk about each one of those for an hour, but let's talk about the third theme, speed. So let's consider a timeline of an attack. So at T0, an attack begins. Then at some point in the future, T1, we detect that the attack has begun, and maybe some global aggregate is off. There's some step function change in some metric that, I'll give examples in smaller groups. Then we go into rule development mode, so we're trying to figure out what is it that identifies this attack. Eventually, we figure out what identifies this attack. The rule is created, and it's enforced synchronously, asynchronously. At this point, new content can't get into the system if the system is working correctly. But we also have this problem that content lives forever. There are accounts that are compromised, and so we want to circle back. There are fake accounts that we want to disable. So we want to circle back and clean up as much of that as possible. Once we're done with that, the attack is completely mitigated, and then they will mutate, and we will play all over again. So these two tasks, rule development and cleanup, are two major ones that we need to, that I'm going to talk about today, that we need to make as fast as possible. So step 1, we want it to look less like this and more like this. Those are our beloved analysts. And those are live shots from the office. So the first weapon in our first arrow in our quiver is the DSL, the domain-specific language that we use. It's an internal Python DSL, meaning that it's actually Python that's executing, and then we add bells and whistles to make it fancier. This is not because Python is a particularly good DSL language. In fact, I've written a number of DSLs, and it's pretty poor. But the original architecture for Pinterest was in Python, so one of the main objectives is to get first-class access to everything in the Pinterest ecosystem. So when you're asking for pin objects and then some transformation on that, and then filter that through some whatever it is, we wanted that to be very easy. We wanted it to be possible, and we wanted it to be easy for us to update the DSL as our needs evolved. So it's an internal Python DSL, but it's great because we have loops and branches and closures and regexes and all the things that you get with Python. So let's walk through this example. So like I said earlier, an event is created when something happens. That event is then considered synchronously and asynchronously. In this case, the rule would say, is this a pin create or a repin? And if not, then it'll just abort and let some other rule take over, or some other set of rules take over. But it is. We'll say it is. So now the next question is does the link that this points at, so when you go to Pinterest, you can click on a pin and it goes to a landing page, does the link that it points at, is it suspicious in any way? Okay, well, so this is obviously not a real rule, although it's, because all of this is a cat and mouse game. But it's not too far off of what some of our simpler signals might look like. So it is a suspicious URL. So now we might ask, okay, in the earliest logins of this user, were any of them from a suspicious country? If they were, then let's look at the details of the pin. Let's say the description. Does it have any suspicious keywords in it? If all of those things are true, then we'll take some action. Silence the user, deactivate the user, various things we might do. Otherwise, we will ignore. Okay, second part of rule development. We want to simulate results and iterate as quickly as possible. So step one, which is what we have right now, is dry run mode. What dry run mode does is you say, here's my proposal, here's my hypothesis about what divides the good users from the bad. Tell me whether, if I were to make this live, what would happen, right? So we put that into production, running against the live rules, just like everything, or live traffic, just like every other rule would. And then we take the results of that, the actions that it indicates, and put them to a system we call pin queue, which is a review queue. Then once enough of those stream by, and we've determined that our false positive rate, the rate at which we're saying good users are bad, is low enough, then we make the rule live and do some statistics, and it turns out it's about 150 for our, I guess it would be our deactivate user. Depending on how bad the action is, if you're wrong, you have a different number, so the statistics change. But this has some problems, okay? So what we'd actually rather do is backtest on historical data. Some of the problems with this, with the dry run approach, are that you have to wait for the attacker to be attacking, right? Let's say you identify that attack has started, and then the attacker goes to sleep and turns off their botnet or whatever it is. You have to sit there, and it's unclear whether is it that my rule isn't good enough, or is it that the attacker has stopped attacking? And even if they are attacking and you do have a reasonably good rule, you still have to wait for enough events to stream by to get that result. So you're waiting a lot, and it's unclear whether you're triggering or not based on whether the quality of the rule is high or not. And then, so you also would like to be able to hone the rule on the same sample of users. So being able to do historical backtesting is we believe, the next sort of step in getting that flat function, the flat results function, maybe a step function down, and there's some other stuff on top of that. So that's coming very, very soon. So we want accurate simulation and historical data. So task two is that we've made the rule live, and we want to clean it up. So we know the signal, at least going forward, but we don't know how to clean up the backwards history. Historically, this would have involved a Hive script where, we've made the rule live, and then we would say, okay, how do we re-represent this in a batch context, in a Hive query or Redshift query, to figure out who's compromised, what content is bad, and so on. This is problem. It's fine. It works okay, but it has two problems. One, it's not very efficient, right? Because if you could say, I already know the signal, please just make it work. That's zero effort, and rewriting it, re-representing it, is greater than zero effort, and greater than zero is greater than zero, so it's less efficient. The other problem is that you potentially introduce errors. You've got a second representation of what should be the same thing, and it's not only just a second representation, it's a second representation in a very different kind of context. Batch context versus streaming context, you might not have access to even the same information. So it may not even be possible to represent that same signal looking backwards. So we want to avoid that. The goal of all of this is to say that we want to treat the past, present, and future running a rule on a historical stream versus running it to develop a rule versus enforcing it in the future. All of those should be the same. We think of that as representational equivalence. So to make this concrete, imagine that we wanted to refine our previous rule with looking at the last 5 logins and say if any of those are a suspicious country, then we'll extra consider, that'll refine our precision. We're more likely to be right now. Well, that last 5, it's sensible to say now what the last 5 are. It's probably pretty easy to find that information. But if you go 3 weeks back in the past and say the last 5, that's a very different kind of question. And so this has implications both in how you're represented in the DSL and what the systems are. So let's talk about some of those consequences. So time comes everywhere in our infrastructure, in our thinking. I mean, and we had to bake it in from the beginning because its tentacles are so deep that it really affects everything. So we think about this property, we call it now agnostic. And what now agnostic means is simply that now is the placeholder for the time of execution. So the rule is going to be executed at some particular time. And what we want to do is not think about now. We want to think the execution time. We want to think about the time that we should have considered this, which is to say the timestamp of the event. And we want to write rules as if now is that event timestamp. So time is implicit in the DSL. We're very careful about that. See in the previous example, there's no explicit representation of time. But it has to be explicit in the system interfaces. Take, for example, feature storage. Let's say you're writing a rule, really simple rule based on rate limits, which are not really a great strategy, but let's say you were writing that rule. So you've got a rate limit, and you say in the last 5 minutes, has this person, has an account created more than 10 pins or something like that, or per second, whatever, figure out some sort of rate scheme. That question is very different if you say the last 5 minutes versus even the previous 5 minutes, or certainly a day or a month or a year ago. So, being able to ask intrinsically the question, give me the most recent relevant history, is important. And then this is bound at execution time to the event's timestamp. So the summary of that is that we want to rewind history and then replay the rule. I put rewind in quotes because that's literally the name of the system that does this. Now, all of that is actually somewhat simple compared to the harder problem of materializing actions and extreme out-of-order delivery. So you've got rules that, take for example, you should have right banned a user a year ago because there's some attack that happened that we didn't realize. So we should have right banned that user. So they're in read-only mode and they have to recover their account so the attacker can't do any more damage. But we didn't. But the user, him or herself, discovers that their account is compromised. They go reset their password. Okay, everything's fine now. Then later in the future, now we say, oh, there was an attack a year ago. Let's go back and materialize let's clean up that attack. So you go back, the rule indicates to right ban. Well, that's actually bad because now the user is going to have to reset the password once again, and every single time you run it, this is going to happen. So unfortunately, I don't have time to get into the internals, but there's a lot of stuff about generalizing that statement, this extreme out-of-order delivery that is very interesting from a systems perspective, but most importantly, the analyst doesn't have to think about this. This just works. Okay, so these things are great, but the problem is we now have a massive system that can blow up on our face. Right? We're taking massive action, largely unchecked, intentionally so, because we need to be able to move quickly. But what happens if we deactivate every user in our system? Okay, that's bad. Even worse, I'm going to claim, is that we don't deactivate every user in our system. We deactivate some small percentage, and then a slightly larger percentage, and then a slightly larger percentage. And over time, we don't realize that we're disenfranchising 10, 20, 30, 50% of our user base quietly, and we never know. Well, that compounds, and it's bad. So let's talk about how we manage that risk. Step one is to understand the drivers of risk. Moving quickly, so not having all the information available to you, but we have to make decisions, right? We have to pull the trigger at some point. So there's a limited amount of information that we're going to work with. So playing with how much do you need to wait for, how quickly can you accumulate information is part of this question. Then the other is whenever you're taking massive action, like you've got a bazooka on your shoulder. If you shoot the bad guys or whatever, like great, but if you miss, you've amplified the consequences of a bad decision. Okay, so mitigation. Approach number one, you could just move less quickly. You could take fewer, less aggressive actions. I'm probably not being very fair to the approaches here. In other words, you're lowering the scale of your efforts. Approach two, which is sort of in conflict with some of the earlier ideas, hint, hint, not going to go with approach one. Approach two is don't limit the speed or scope of the action, but be able to undo the consequences of a bad action. we choose approach 2. We trust our analysts to make good decisions and launch rules and apply excellent judgment, and then we give them the tools to fix and measure them. But it's actually not even just an analyst thing. Actually, probably the most recent use of this, certainly the most recent use of this, so we had a model serving infrastructure that had a race condition between 2 models, and we didn't realize it because it was very subtle, right? Race conditions are tricky, where it was serving the results from one model for another model. We figured this out after a couple of days, and thankfully, because we have complete visibility into all the actions that are being taken, we were able to know that, over this time frame for this model, go push the button and undo all of the consequences of that model. So, certain things can't be undone, like sending an email and so on, but as much as can be undone, it's relatively easy to do so, which is how we pay a smaller risk premium. We also have mechanistic feedback. So there's a passive loop, which we basically sample actions that are taken from rules over time. If we get enough of a statistical signal that there might be something up with this rule, that its prior has changed, then we would go potentially do a re-review of the whole rule. The other one is an active feedback loop. So if we get enough confirmed appeals, we deactivate people, they write in, we confirm their appeal. If we see enough of those, then we suspect again that maybe the rule is broken, so we can re-review it. From an infrastructure perspective, this requires that all actions are reversible at any time. Like I said, you can't unsend email, so some things are not completely reversible, but this is the goal. It's easier said than done. Talk more about that later. So in summary, the core capabilities that we're after right now are flexible DSL framework and rule engine. Our DSL framework is meant to be versioned, language agnostic. We hope to implement Haxel, and there's a really great feature extraction DSL inside the company that we want to get in there for the feature extraction phase. But so this whole framework is meant to be very, very flexible. Rewind, which is what allows us to consider historical timeframes and take action on them. And undo, so push button mass action of broken actions. Next up, we need to further improve the rule development. We've been focused for the last 2 years on infrastructure, where we've got some relatively simple machine learning stuff in there, but we're about to get a lot more sophisticated with that. A system called Cerebro. This is a rule development model training pipeline that is implementing a portion of our strategy that is very focused on the mind-machine approach. And basically, we're going to introduce some semi-supervised learning techniques into that pipeline. I'll talk more about the capabilities of that in some future talk. We also it's great to talk at conferences like this. It's great to write blog posts, maybe papers, whatever, but the rubber meets the road with the code. And so Pinterest is very big on open source, actually. And so we're hoping to open source all of this, not necessarily immediately, but once we get all the interfaces hardened, perhaps we can increase the herd immunity if others are interested in these kinds of tools. And also, don't be a stranger. We've been doing this for a little while, but there's a lot we can learn. Maybe there's some insights that we've had. Like we're always open. We're largely Facebook and Yahoo and Twitter and so on have been very open with building a nice little community and others. So let's talk. This is the team. Teamwork makes the dream work. So with that, are there any questions?
With all the systems in place, what today is like the average time an ad is, spam ad that comes up? How long does it take it by average to bring it down?
Yeah. I actually had a slide on the various metrics that we've been sort of accumulating and tracking over time. It's certainly well with under a day on most attacks. Jessica, what would you say the average time that pin is up?
I would say definitely within a day, maybe 5 hours.
Yeah, a couple hours, 5 hours, something like that.
Follow up on that is how many users do you think have been exposed to that?
Yeah, that's another metric we track, which is actually that is our core metric now. It's percentage of monthly active users who have a spammy user experience, MAUs with the sucks. And that is, what is that now?
What is the average?
Yeah, about 1%. So we can do better, right? But I think we're at basically the limits of our current technical approach. We need to get that rule development and visibility up a lot to take that next step function. And just cut me off whenever I'm supposed to be done, by the way.
Hi, can you talk about the spam ops folks, like what their training is, what their background is? Do they have a very sophisticated interface that they're looking at features at, or are they just looking at kind of a user experience interface? Thanks.
Yeah, so Part of the reason that we believe in this kind of like mind-machine strategy is that it's very hard. It's going to be very hard to get a single person who is a systems expert, a machine learning expert, and statistical expert, passionate about the product, really understands the product, and wants to get in that adversarial fight every day, right? So division of labor is sort of the strategy. So our analysts have because of the DSL, they're writing in Python, so they've got at least a little bit of development experience, but they're not like engineers in that regard. But they're very passionate about the product. They have some, they're doing statistics and so on. There's a lot of like batch queries right now, especially that they're doing before we have everything in the streaming context that's immediately accessible to them. But it's not, so like as opposed to like a PhD in machine learning, right, kind of approach. We're specifically avoiding that approach.
Do you guys have anything specific to cover languages outside of English?
Yes. So the kinds of signals that you'd look at outside of English were, so there's the content-based stuff, but there's also, what is the behavior? So we should talk about specific signals later, but so behavioral signals, network topology type signals, other kinds of things. Yeah, you basically get away from the content itself and more toward the behavioral.
You mentioned user action and actual pin content in appraising for spam fighting type signals. In what way is landing page quality evaluated within this model?
So landing page quality is, well, it's interesting because there's a couple things about the landing page. One is that they will try to do tricky things like redirect and obfuscate, and they'll do different things with different browsers and so on. So just detecting that weirdness is afoot is certainly part of the equation. They also will use templates, like they'll use the same templated thing. Maybe it'll have some variation, or sometimes it doesn't have any variation at all. So that's kind of the data side. Now, quality side, quality is where it gets actually kind of tricky as to know whether something is spam or not, because we've had examples where it's like it's not. You get the dress, like it's like a wedding dress thing, right? Like you get the dress, but a lot of people complain about it, and the website itself looks kind of shady, but you do actually get what you paid for. Like, are we in the business of calling that spam or not? That becomes kind of a tricky policy question. Where it's very clearly spam. Yeah, I mean, you're looking for, what again, without going into too many specific signals, we can talk offline. Maybe not so much the quality, but the actual content of the page is relevant. Figure out, are they using certain kinds of words and in what ways and so on.
Hi, could you talk a little bit more about the source of ground truth for your training data? Like if you want to assess the recall of your classifiers, where do you get the true spamminess or the true hamminess?
Right. So right now, like I said, we've got relatively simple ML integration because we've been focused so much on the infrastructure half of it. The pipeline that we have right now is, I think, a pretty standard one, which is that there's a decision made in the system, and then that, by either a rule, like basically our rules are treated essentially as ground truth, unless they're undone. The precision requirement is so high that that's essentially ground truth. So you can then train a classifier based on that. We had a large training set from before that is the basis of a decent amount of the training. But right now, like I said, it's relatively simple. We would essentially treat the decisions that we're making both manually and through Stingray as ground truth.
Do you use technology like Spark or Storm to run the Python DSL?
Yeah, we use both actually. We consume the events off of the Kafka stream using Storm. Then that goes into, so basically the problem with the stream orientation is that we want to make progress where we can, but we want to guarantee delivery at least once. And so the problem with the stream orientation is that if you only can store an offset, then you reach a record that you can't process. Let's say it's a user login versus a pin create. Well, those two might have very different models that they're dependent on or systems that they ultimately query. So one might be down, but we want to make progress on the other. So what we do is we offload immediately from Kafka into SQS, which is a message-oriented interface. And then from there, we do a bunch of things, and then ultimately we have a mass action taking system that uses Spark, and the rewind system that I was talking about uses Spark as well to pull events out of S3 and then simulate history. Cool. I think that's that. Thanks a lot.
Hi. So I saw a lot of nodding to Chris's talk, and this basically further illustrates my point. Learn some new techniques of spam fighting. Go meet people that you think you'll probably reach out to later, and just have fun. And we also have an amazing spam operations team here at Facebook, but we probably should bring them to Vegas, just like Pinterest.